This is going to be an extension of what we learned in Chapter 20. Now, in Chapter 20, we focused on these three sorts of non-homogeneous functions. Ones that had an e to something x, ones that had a polynomial, and then ones that had sines or cosines. Of course, we also looked at combinations of those, and we saw what we could use as our guess and then how to develop that into our particular solutions. But what if our non-homogeneous components was something like this? Those do not fit any of the ones that we were just considering. Now, the technique we're going to take a look at is going to focus on finding the general solution when we know two linearly independent solutions. Usually we can get those from solving the corresponding homogeneous equation. And as you probably know from previous experiences, this would be a fun thing to have in a notebook. So let's see how the method works. Here we're asked to solve this second order equation. We're already given the homogeneous solution. Let me just remind you, we could have found that. Notice this is an x squared y double prime, a 2xy prime, 2y. Had this been a 0, then this is our Euler equation. This one would have come out to be an r squared minus r. This one would come out to be a minus 2r, and this would be a plus 2. And the indicial equation then would be r squared minus 3r plus 2 equals 0, which, as we know, would factor into r minus 1 and r minus 2, which gives r equals 1 and r equals 2, which tells us that our homogeneous solution would be some constant x to the 1 plus some constant x to the 2, which is what they gave us right here. Now, anyway, you're not asked to solve that. You're given that information. However, again, in our guidelines that we're about to follow, this is what we're calling y1, and this is what we're calling y2, our two linearly independent solutions. So here's where we're headed with this. We need to find the u and the v that would fit here. And to do that, we have this special relationship to consider. We need to solve the system of linear equations given by y1 u prime, y2 v prime equals 0, y1 prime u prime, y2 prime v prime, and g divided by a. Let me point out that this is what we're referring to as g, and this is what we're referring to as a. So that's the g over a down here. So anyway, the system of equations then would look like this. The y1 is x, the y2 is x squared, the y1 prime would be a 1, the y2 prime would be a 2x, and then the g divided by a would be 3 root x over x squared. Now, as your textbook author rightly points out, the main flaw or the main issue in using this technique comes in solving this particular system of equations. So we're trying to solve for the u prime and the v prime, and this could be done by hand. I'll just point out that it would probably be best done on a TI-89. So here I've taken my TI-89 and solved the system of equations rather rapidly, and I came up with the two solutions. U prime equals negative 3 x to the negative 3 halves. That's what we see right here. And v prime is 3x to the negative 5 halves, which is what we see here. Now I can show you in class if you need help in solving that either on the TI-89 or by hand if you do not have a TI-89. So once we know u prime and v prime, we then do the integrals of those. So here's the integral of u prime and the integral of v prime. So there's the u and the v. Once we find u and v, we can come plug those back in to find our particular solution. So substituting those back and doing some simplifying, we get our particular solution. Now the last step is to combine the c1x, the c2x squared, and the 4 root x all into one solution. Your textbook author also rightly points out that many times when you get to this step, some of these may be things that can be put together. That is not the case here, but many times it will be. So let's go through this second one, given y1 and y2, and see what it looks like. So again, this is where we're headed with that. Our particular solution would be u cosine x, v sine x. We need to find the u and the v. We do that by taking the determinant that's formed with the y1 u prime, y2 v prime equals 0, y1 prime u prime plus y2 prime v prime equals g over a. Now, again, for this particular problem, I'll point out this is G and this is A. And so here's the system that we have. We, again, will solve that utilizing our TI-89. So we end up with a u prime equals negative tan, v prime equals 1. We need to integrate those to find the u and the v. We then substitute those into what we had in number 1 to find the particular solution. We then want to combine the particular solution with the y1 and the y2 to find our general solution. And unlike what I was pointing out in the previous one, which didn't apply there either, there's not really anything here that can be combined together.